Hello, everyone. Welcome to our presentation for our paper for the IDDM 2025. That's going to be hosted at Lviv Polytechnic. Our paper is Hierarchical Classifier Implementation upon YOLOv8 and Synthetic Data Usage for Medical Instruments and Their Sorting. The 5 authors here are Mysiuk, myself, Liliia, Lyashkevych, Petro, Kulyk, and Iryna Mysiuk. All of the authors except for myself are from the Ivan Franko National University of Lviv, and I myself am from Centrale-sur-Bellec, which is the engineering component of Université Paris-Saclay in Paris, France. So first, we'd like to start off with the problem we're trying to solve. So this is sterilizing tools at the First Medical Union of Lviv and generally to all hospitals. So first we look at the life cycle of how tools get sterilized. They start off in the sterilization department, are then transported to surgery where doctors and nurses will use the tools. They're then transported back. From surgery to the sterilization department to be cleaned, and within the sterilization department, they're sterilized. Despite this being the shortest text we put here, this is the step that has the most components, or a step that has many components. During this step, we first have to sort the tools. The way it's done currently is it's being manually sorted by this team of 7 people at St. Pantaleon in specific, where they're sorted into bins of similar tools. Then they're rinsed by hand, so they're hand washed. Then they're machine washed in industrial machines, and then finally they're sterilized fully, where they're heated to eliminate any remaining microbes. What we can look here is that in this first step, this can be optimized using artificial intelligence. We have many frameworks. So we have YOLO, we have the TensorFlow model, object detection, Model Zoo. We have many existing frameworks to optimize these to sort objects. So what we decided to do is we decided to investigate this. Naive object detection models are a perfectly valid solution for this. They work well. They have a high, especially the ones that are currently online. They have high accuracy. So on a balanced data set, they can give up to 95% accuracy. And again, because TensorFlow and YOLO are so optimized, there's very quick training that we can do, even when we're as resource constrained as we are. However, 95% is good, but it still requires there to be supervision, because 1 out of 20 mistakes is still a solid amount, and is something that we would want to try to improve. Right now, our main issue with why we also decided not to do this was because of how long data capturing takes, or not data capturing, but the preliminary data collection takes. In general, the first collection is done in 2 steps. You first have to take the image, so you have to take a picture of it. That about 20 seconds per image. You then have to give it a title, and then also labeling. This is the complicated part, and this is the part that really is extremely time consuming, and it takes up to a minute per image. Anybody who's done object detection knows that when you're labeling this XML and you're drawing this bounding box, and you have to be pixel precise as to what the edge of it is, as to what like the top left corner and what the bottom right corner are. Everyone knows you have to be very specific, and it takes lots of passes to get through. This is like 1 minute per object per image. So it's like when you have images that have multiple objects on them, it might even take longer than this. Unbroken in the First Medical Union doesn't have a massive team of data scientists to help us label this data. So instead, what we asked them to do is we asked them to take pictures of their tools that they're going to use, and only in the 2 different main angles. So from the top, and then mirrored, so from the bottom. And so that would be the 3D like image that we asked them to take on a green screen, so that then we could automatically label and augment the data to provide to our model a much larger data set than just the 2 or 3 initial pictures for each object that was provided to us. So we had them take an image on a green screen. We extract it using a mask, simple in Python, using a mask that detects the minimum x value of our object within our green screen, maximum x value, minimum y value, maximum y value. And then what we do is we augment that. So first we apply noise to the object, standard Gaussian noise. Then we apply random sizing and scaling to the image. For the sizing and scale, what we decided was to take between 0.75 and 1.25 times the size of the initial image. That's purely empirical. It could be anything else. For rotation, we decided to rotate it, again, in a uniform distribution, anywhere from 0 to 360 degrees. So it could be rotated however much it needed to be. Then also put a random background behind it, as well as implement a shadow, and then vary the number of objects per image. Here, this is what an example of the synthetic annotation will look like, where we'll have will have the name of the object with the bounding box on it, which was all automatically done from the initial green screen image. Here's another one where we had two images on the same one. These were taken from opposite. So yeah, so we can see here that the reason this is slightly different is these were the two different visibility edges or pictures of the image that were taken by Unbroken or by our team at the First Medical Union that were both randomly selected to be put onto this image. So that's why it's not the exact same one, but it's the same object. We also decided to, when we were doing this, to throw in dummy objects to increase generalizability. So here we can see a detection. We can see like one of our example predictions, which includes both the medical tool here as well as two other ones that we threw in. So a coin and an astronaut. It detected all of them well. They all far exceeded the confidence threshold of 50%, but they only one is useful. However, this was done so that we could generalize, so that our feature space would be more intact and more generalizable. Another thing we decided to do is we decided to do hierarchical modeling. So take into account the relationships between tools. In general, what we found was searchable tools are specialized, or they're categorized into cutting instruments, holding instruments, retracting instruments, and suturing instruments. And these were like the empirical values or the empirical categories that we found. What our assumption is that a model would confuse these more than others. We have in a paper, a different paper, a way of doing this computationally or numerically. But here, this is just our general like theory here. So what we decided to do is we could make a hierarchical classifier where we'd have a shared backbone that would have the feature space of all of the images combined, but that it would classify, it would not output as a naive classifier would. It wouldn't output the object directly. It would send it to another specialist. So it would say, instead of this being this object, it's in this family, and then send that to a specialist to identify that. So here, for example, if we have our families ABC, so these are more similar, DE more similar, FG more similar, and H just by itself, we would have our shared backbone send this information or send the picture to the specialist 1 if it detected AB, if it thought it detected something in the family of A, B, or C, to specialist 2 if it thought it detected something in the family of D or E, to a specialist 3 for F or G, and then to a redundant, but because we're using recursion here, one-way specialist of H. This is what our training looked like for this. We ended up with very high mean average precision, and then when we were looking at 95% confidence, we still ended up with a very, very high value. These were the numerical values we can see, as well as the box size distribution. So how well it detected the bounding boxes, how well it as well as how well it predicted. So how confident it was. Here's some sample predictions that it had. So here's of course with the dummy images. So we have our astronaut here. We have this here. It managed to detect. It always detected something. Or at least from the images we could find, it always detected something. We'd like to acknowledge our gratitude to the IT department of the Lviv Territorial Medical Union, so 1TMO, for their support, and with special thanks to our clinic reference, Petro and Maxim Nakonechny. I'd also like to personally thank Razom for Ukraine, who made this connection between myself and my Ukrainian colleagues here possible. Just to quickly discuss some limitations and future expansions, as well as our conclusions. We have it correctly identifying our annotated instances with a very high mean confidence and mean average precision at 0.5. However, we have to note that hierarchical systems do increase our computational complexity, and will thus potentially, and may also thus suffer from error propagation. Where if the first model detects the wrong family, then the specialist will of course also will not detect the correct object. Also, our use of synthetic rather than real imagery may limit the direct clinical applicability. We're going into trial with the clinic very soon to ensure that everything works. We also, however, we say that it can be integrated into clinical workflows to support automated sterilization management, instrument inventory control, and tracking of these objects between operations, which both enhances efficiency and patient safety. Thank you.